Argentina por 1 año y medio y aprendí español argentino, pero hoy no estoy preparado para dar una charla en español. Así que you will have to put up with my English. I'm sorry. So today I'm going to talk about some of the work that I did in Argentina as a postdoc there in the museum in Buenos Aires. And now I'm currently living in Pennsylvania in the US, where I'm teaching as an adjunct there and continuing some of this work and to write and publish some of this work. So, no.
¿No? No funciona.
Tal vez no, del lado derecho. Tal vez esté acá.
Está prendido porque funciona bien.
Oh, un momentito, ya vi. Ya.
Okay. So, just to start off, Opiliones are daddy longlegs or harvestmen. They're not spiders, they're arachnids, but not spiders. They have no venom or silk glands, so they don't produce either venom or silk. They eat whole food particles. One of the synapomorphies for the group is that they have these repugnatorial glands, which are located on the body right here. And you see they use, in some species, they have this behavior where they use leg 1 to pick up the droplet from the gland and hold it out on the leg and wave it in front of them as kind of a defense mechanism. They have tracheae, not book lungs, and they have a true copulatory organ. You can see 5 different forms here. We call it a penis, being a true copulatory organ, and so there's a lot of diversity in the morphology of the penis of the harvestmen, and so this is a good character for defining certain taxa, especially at the family level. So my focus in my work is mostly on this group of Laniatories, which is very diverse with over 4,000 species, and so I'm looking at 2 different groups. One being this superfamily, the Samoidea. It currently consists of 3 families. 1 is African, 2 are neotropical. You can see some of the diversity in the body form here, as well as the size. This is a couple millimeters in length. Here, the animals are less than 1 millimeter. There's 5 of them inside of a microgenitalia vial. So very tiny animals. The scrofula on the leg is on some of the species, in some of the families, but not all. And the neotropical families have this glandular area. It's a sexually dimorphic character that we're using to delimit the families. And so I'll talk more about this structure on the leg a little more later. So the family has 52 species. Just this one family, Samoideae, has 52 species and 26 genera. 33 of them are in the neotropics, and 19 are in the Southeast Asia and the islands in the Pacific, which is a kind of an interesting distribution. The body shape, we can use body shape, the presence of scrofula, and some of the male sexually dimorphic characters to tell species apart, to define genera, and we're using them more now to look at the delimitation of families. So the objectives of my work in this project were to just discover and characterize some of the diversity of this group, which is poorly studied. Looking at phylogenetic relationships using both morphology and molecular data. We were testing taxonomic hypotheses like, are families monophyletic? Are the lineages on the islands monophyletic? Because we're studying these groups across the Caribbean islands. So we're looking at whether these groups, as they're currently defined, are monophyletic or whether we need to redefine them. So that's kind of one part of it, and then the other part is looking at biogeography. So we reconstructed ancestral areas on dated phylogenies. So we estimated divergence times, tested biogeographic hypotheses, and looked at the relative roles between vicariants and dispersal in the islands. So kind of a very brief overview of the methods I used. We extracted DNA and amplified a few genes, mainly 18S, 28S, CO1, and H3. We aligned those sequences and trimmed them, selected the best model for sequence evolution. We used both maximum likelihood and Bayesian analyses to reconstruct the phylogenetic trees. And then we estimated the divergence times in beasts and used an R package called Biogeography to estimate the ancestral ranges and look at some of the biogeographic patterns. So our first question is, are the families of Samoyedea monophyletic? Currently, as I said, 3 families. Bianthidae is in Africa. That's not really the focus of this, but we had some representatives. It's almost an outgroup for us in this study. We're looking mostly at Stigmatidae and Samoyedea here in the Neotropics. So, under our current taxonomic system, this is what the families would look like. And as you can see, based on the colors, the blue being Bianthidae, the green Stigmatidae, the yellow Samoyedea, none of them are monophyletic. So, obviously, we have a problem with our classification system. And so we kind of knew this from the start. We kind of hypothesized that they are not monophyletic, but we did get some surprises back from the molecular data. So we kind of took this and looked at our morphological data, and we looked at how can we best define these families. And so we've come up with a classification system that gives us Bianthidae in Africa, along with 5 neotropical families. So now we've gone from 3 families to 6. And this is really the limitation of these families based on morphology. We're using this molecular data to support that. So we have Stigmatidae, Stenostigmidae. Stenostigmidae was formerly a subfamily of the African Bianthids, so it's raised to a family rank here. We have a new family, Neoscrotolemidae, a new family, Homunculidae, and the existing family, Samoyedea. But all of them redefined based on different characters than we previously used. There are still a few taxa that don't fit into the way we classify these families. So we do still have a few Incerticetus taxa. And really that's a problem of our sampling. We don't have a lot of samples from South America. So with better sampling there, we might see some of these taxa resolve. So we have one here, the very base of the neotropical group, and that is from Ecuador. It's one of our only South American taxa, but it doesn't resolve well with any of the other neotropical families. We have this one from Mexico, actually I think it's in Chiapas, and it just doesn't resolve well in any of our families, even though it does appear to be related to this group here. So it's interesting that it's kind of an early diverging lineage to this group. You can see some of the body forms here. They have pretty large bodies in general. Some of them have spines between the eyes. So you see the eyes in the front of the animal here. The stigmatids have extremely long chelicerae and pedipalps. We say they're hypertelic. So based on this analysis, we see that Samoyedea is a monophyletic group. The neotropical Samoyedea is monophyletic. And we have several monophyletic families within the neotropics, and that's kind of the focus of this work. I'd also like to point out that we have more than 60 new species to describe. So just looking at the diversity, discovering that diversity within these families, now I've shown you that we had 3 families that we had described, and now we're raising 1 to family rank, describing 2 new, so we're increasing that to 6 families. The genera is the same, same pattern. We have what we see as 5 new genera, and then if we look within those genera, for example, Actolema, 1 species was described from Mexico and 1 from Jamaica. So we had 2 described species. We know of at least 8 new just in Jamaica alone. And the lineage that's in Mexico is actually a different, kind of separate lineage, but they're sister to one another. The Neoscota lemon, most diverse in Cuba, previously 2 species described. We know of 20 new species that we're working on species descriptions for. And Homunculus, 1 species, we know of at least 6 new species. Just incredible unknown diversity in the neotropics. And so just to give you a picture of what that looks like on the island of Jamaica, the 1 species that was described is from the eastern part in the mountains. We took samples from the Cardio project, which sampled from all the Caribbean islands and parts of the mainland. And from their samples, we found 8 new species just in Jamaica. So very diverse. Okay, so going back to our phylogeny now. If we look at the way we've defined these families, we have several characters that are really important for delimiting them morphologically. So as I said earlier, this group of neotropical Samoidea, they have on leg 3 of the males, it's a sexually dimorphic character. On leg 3, the metatarsus is enlarged. And so here in the Stigmatidae, you see this enlarged area, and right here, you see a pore, a very large opening. So this is glandular, and it's distinct within each family. So if we look at Stenostigmidae and Neoscotolemidae, they're sister to one another. We see a pretty similar pattern in this structure. You see a very long invasion of one leg segment to the other. So you see CD inside of that structure, all those CD, the lines of CD going this way. And then among those CD there are pores, and they're spread out across this entire organ in these 2 groups. So very similar morphologies there. If we look at the Homunculidae and the Samoidae, they also have kind of a similar pattern where now it's very elongate, but it's also depressed. The CD are starting to aggregate more to a distal location, and the pores are also aggregating more. And so here on this leg, right here, you have an aggregation of both CD and pores. And so it's a very interesting structure that's pretty conserved within families. And so I think we can use this to delimit those families morphologically. So one kind of anomalous taxa, even though I show it here in the Homunculidae, this genus Americanatum is different in many ways than anything else in this phylogeny. And one is that it doesn't have this metatarsal organ. It seems to be secondarily lost. It also has a stridulatory organ on the chelicera. So this is kind of the mesial surface of the chelicera, and both sides of each chelicera has one of these, and so as they rub together, they stridulate and create a vibration, but no one has studied what this is used for. It's sexually dimorphic as well, so it's only in males. So we can guess that it might be a reproductive behavior. So Americanatum is kind of tricky, and we aren't quite sure whether it fits in for the Homunculidae, but I'm gonna leave that go for today. That's something we're still working out. The penis morphology, as I said, is very important, and it's important for systematics, and it's also important for functional morphology. So here we see a penis of Stigmatidae, the species Zygobunis rufus. Here it's in its normal form. It's just in alcohol. It's in the state that we see it when we dissect it. But if we take that and we put it into hot lactic acid and back in distilled water, some of these genitalia actually expand or inflate. So this is the same penis but inflated using that method. And so you can see these points, the red dot and the 2 yellow dots, when expanded, these points move up. And so they move out from within the sort of protective casing of the truncus of the penis, and it kind of unfolds and expands, and this is what it would look like in its state when it's actually being used. The stylus is where the ejaculatory duct would terminate and the opening would be at the tip. These conductors in this particular group, they may be separate like you see here, or they may be fused together. And so that's kind of an important character that we're using to define these families. So if we look at the genitalia of all the families, you see the one I showed you here for Stigmatidae with the separate conductors. So you see where the arrows are, these are the separate conductors, not fused or very partially fused right at the base. And in the other group, the Homolinculae and Samoidae, we see fused conductors. So here we have a fused conductor, the stylus sits behind it, which is separate from the conductor still. Here, fused conductors, but the stylus behind it. This one has interesting sort of wing tips that extend upward. And so the conductors are fused. So we see a nice pattern here with the genitalic morphology. So to conclude with the systematics part of this study, we see that Neotropical Samoidea is monophyletic. The families and some genera are not monophyletic and require extensive revision. There's a huge amount of diversity that remains to be discovered. And so we're working on describing these 3 new families so that we can later go back and describe the new species that belong in those families. But first, we need a better picture of what the family diversity looks like. We realized most species are short-range endemics, so they have very narrow distributions. You don't have to go far and you can find a completely different species, maybe in another mountain range adjacent to one that was previously sampled. So we need better sampling at smaller resolutions to be able to really understand the full extent of the diversity. There are some taxa that remain problematic, but we know that we just need to go and sample in some of the places that are poorly sampled, like in South America. There are plenty of species that are described from there, but that we didn't have fresh materials for our molecular phylogeny. So we know we're missing a lot of taxa from South America. So what about the geographic distribution of these families in the Caribbean? So we look at the distribution of each of the families I just told you about. Stigmatidae, it's interesting if you're studying biogeography in Central America, and they extend all the way up to Mexico, but our samples are relatively poor for this family. We weren't really focused on it. That's not really a focus of this study. It could be a great project in the future. Stenostigmidae, also very diverse, occurs in Cuba, very diverse in Cuba and Hispaniola. Would be great for biogeography, but again, wasn't the focus of our study. So we focused on Neoscutolamidae, the Homolinculae, and the Samoidae. And we looked more closely at these families and how they're distributed through the islands. Okay, so why are Opiliones good biogeographic models? They're very old. They have ancient origins. We have fossils that date back over 400 million years. You can see a recent paper from 2014 that did some micro-CT of one of those fossils and had some really good images. They're globally distributed and relatively abundant, so they're relatively easy to collect. The smaller ones can be quite tedious. You're sifting through litter, but in general, compared to other groups, they are relatively abundant. They're also short-range endemics. They have poor dispersal mechanisms. So here you see a spider, and I don't know if you can see from out there, there's a line of silk going up right here. And that is a line that is letting out, and it's catching in the wind. And when the wind picks that silk line up, it's going to let go of what it's holding on to, which is actually a wooden post that is completely covered in silk. So this is all spider silk on this post. And this spider is going to balloon. So that's how spiders disperse, some of them. So harvestmen don't have this kind of dispersal mechanism. And so when they reach islands like in the Caribbean, it's pretty interesting to look at how they got there. They also have specialized microhabitats. They usually rely on very moist and humid habitats, and so in the tropics they tend to be much more diverse. They're great for studying world biogeography, so A study from about 10 years ago looked at world biogeography, found patterns of species that are related across Laurasia, across tropical Gondwana, across temperate Gondwana. So we can look at world biogeography. We can look at phylogeography. So this study looked at a very small area in western North Carolina in the Appalachian Mountains of the US. And it looked at one species and the different populations that are occurring in those mountains. And so we can see patterns within populations within a single species. And they're also great for island biogeography given their poor dispersal mechanisms. And so you see MacArthur and Wilson here. And the idea that as you go further from the mainland, islands that are further from the mainland here, you have fewer species. Close to the mainland, you have more species. Smaller islands, you're going to have fewer species. Larger islands, more species. So we're looking at that interaction, but we're looking at it on a longer time scale. So we're actually also considering the species that are only on those islands and that the lineages that colonize the islands but then undergo speciation within the island. So you have in situ speciation on islands where this model doesn't account for that. Okay, so we're looking at what we have with Opiliones examples of adaptive radiations. Adaptive radiations occur when species invade an underexploited environment and undergo that rapid diversification, right? So the Hawaiian Islands are a great example of this, and they're well studied in comparison to other island systems. You have the birds, the honey creepers, more than 50 species in the Hawaiian Islands. You have fruit flies, over 500 species. You have the happy-faced spiders. So great examples of adaptive radiations in a relatively young set of islands. But we don't have any harvestmen in Hawaii, so we can't really study adaptive radiations in Hawaii. So we look to islands in the Caribbean. But the Caribbean has a very complex history that begins about 100 million years ago. Between 100 million years ago and about 45 million years ago, there were islands forming in the Caribbean and then being submerged again. So we call those evanescent islands. They're there for a while and they get submerged again, depending on the uplift of the land or the rise or fall of the sea levels over time. So it's very complex early on. And then about 45 million years ago, we sort of have islands that popped up that have remained since then, at least pieces of islands. And so we have a pretty, like I said, a pretty complex history there, and it involves both vicariance and dispersal. So one of the vicariant hypotheses is the Garlandia hypothesis. This is the Greater Antilles Ave Ridge land bridge, which is hypothesized to have been present about 35 million years ago. So you see the present-day Caribbean. If you look in the satellite image, you see this, this piece of a ridge that is now underwater, and it's hypothesized that that was once the Aves Ridge, and it connected South America with some of the Greater Antilles. So this hypothesis, there is some support for it. There are other people who argue against it. Whether it was a complete land bridge or not, it could have just been an extension of the land that allowed animals to get close enough that if they were able to disperse over water, they might have reached the islands much easier. So, so this hypothesis kind of plays into what we're looking at in the Caribbean. So again, we have these complex factors, the Proto-Antilles, the evanescent islands. We have connections between islands. We have the meteor that struck about 65 million years ago near the Yucatan Peninsula. And we don't only have colonization of the islands, but if we have speciation happening within the islands over millions of years, we also have the possibility of reverse colonization. So species from islands could colonize the mainland. And so we have to ask the question that these authors ask, are islands the end of the colonization road? And so in this biogeographic study, some of the analyses we used were by estimating divergence times using BEAST, and then running those time-calibrated trees through the R package Biogeography bears, and looking at several likelihood models within that package, and coming up with a pattern of biogeography that might match what we're looking at in terms of geological history of the islands. So the age estimates we calculated are based on two data sets. The first one is the same data set I showed you earlier that we used for the systematic study. So we used 3 genes, 18S, 28S, and CO1. And we had 2 calibration points. We have a fossil, which is actually an important point with this group. We actually have a fossil within the Homunculidae that's from Dominican amber. We also used a secondary calibration from another study on the Laniatores, which was a phylogenomic study. So we have 2 calibration points for that study. We also used a second data set that only focused on this genus Neoscrotolemon. And we sampled the genus a little more broadly and only sequenced 2 genes for more taxa. We used CO1 and H3. And we used the calibration point we used for this data set was an estimate of the clock rate for CO1, which comes from a paper from 2011, and they were able to estimate an approximate rate at which this gene might accumulate mutations. So we can use these 2 data sets and compare the results that we get to see how each performs. So here you're looking at that first data set, a time-calibrated tree that has been run through Biogeography. So you're looking at the ancestral ranges. That's the colors and the letters here, but don't focus on those too much. Let's look at the origin of the neotropical lineages. So this monophyletic group that is the neotropical Samoidea, the origin is around 80 million years. That kind of matches up with the timing of the breaking up of Gondwana, the split between South America and Africa. And so, we're kind of in the ballpark of that. If we look more closely at just this family Samoidae, let's just focus on that. We have 2 groups that have formed. There's one in Mexico, in Chiapas, and in the Yucatan, and there's another that is in Central America. I think this sample's from Costa Rica, and Jamaica, and Hispaniola. So we have these 2 kind of sister lineages that formed, and so we're kind of looking at the dates of those. The origin, 52 million years, kind of matches up with the formation of the earliest islands that have remained, or at least parts of, have remained in the Caribbean until today. So, let's see. So, the other interesting thing about this group, if you look right here, this taxon, Badessa, is not actually neotropical. It's the only one we have from the Pacific Islands, but it is monophyletic within this group Samoidae. And we know that that taxon, or that lineage is in both Samoa and Fiji. And that's where the family gets its name, Samoidae. The first species was actually described from Samoa. But we believe that it has neotropical origins and somehow has managed to reach Fiji, Samoa, and possibly Australia. We're not sure that the Australian species actually belong to this family, but we are certain that the ones from Fiji and Samoa are part of this group. Our date estimates put it at about 32 million years. And it's interesting to compare this to another group that has been studied, which also shows a similar pattern of neotropical origins and dispersal to the Pacific. But this lineage, the Zamoxidae, has actually undergone adaptive radiations on many of the islands here in the Pacific. And so they seem to be much more diverse. Their age estimate was 82 million years when they arrived in the Pacific. Maybe they are older in the Pacific, and that's what allowed them to undergo these radiations and colonize multiple islands, whereas the Samoidae have only managed to successfully colonize a couple. But it's still quite impressive that they've made it all that way probably by rafting. We don't know. So, looking at the second data set then, which only focuses on that genus Neoscotolemon, you see the distribution map that we've sampled. So all the circles are ones that we've sampled. The blue circle in Jamaica is an early diverging lineage, and we actually have 2 species from there, but we were only able to get molecular data from one of them. And we know that there's also one in Costa Rica. It's either Costa Rica or Nicaragua. It's somewhere in a cave there, but we have the specimens from old collections. We just weren't able to sample them for the molecular study. But we know it's closely related to this Jamaican species, so we'd like to go there and get that and add it to this phylogeny. So the most recent common ancestor, Neoscotolemonidae, we're looking at about 50 million years. And then if we look at just the genus that is most diverse in Cuba, we have, an age estimate, the origin at about 34 million years. Kind of matches up with our Groenlandia hypothesis. Unfortunately, we don't have any samples, or we don't even know that they exist in South America, this lineage. So whether it arrived by way of South America or somewhere else, we're not sure. But we can kind of look at the dates at which they started diverging and undergoing speciation within the group. What's really interesting about this group, Neoscotolemon, though, is that we see all of these red species are in western Cuba. Then this one taxon is from eastern Cuba. And then we have one taxon, one species from southern Florida and one from the Yucatan Peninsula. And these are relatively young divergences. So what this indicates is that there was probably some dispersal out of Cuba to southern Florida and to the Yucatan, much like if any of you are familiar with studies of the anoles in Cuba, they have the same pattern. They dispersed out of Cuba to parts of the mainland and continued to diverge. And so we see species in southern Florida and throughout Central America that are related to the species in Cuba. So another interesting thing here is that this species in Jamaica, being an early diverging lineage, Jamaica, western Jamaica at least, is relatively old and was once much closer to this Nicaraguan, this area of Nicaragua, which kind of is a plateau, which is now submerged. But western Cuba was much closer to that at one point. So it's possible that that this early diverging lineage in Jamaica is related somehow to something in Central America. That's why I'd really like to go back and find that species from that cave. We compare these dates back to our first data set. We can see we're kind of in the ballpark on both. 50 million years for the origin of the family, 58 in this analysis, 34 million years for the origin of the genus, 29 in this analysis. So using both data sets with completely different calibrations and genes, the molecular data being slightly different, we see approximately similar age estimates. Okay, so from our biogeographic studies, we can conclude that both dispersal and vicariance have played important roles. We need to look at each of these families individually to really see the patterns across the islands. We know at least one island, one lineage has successfully dispersed across the Pacific, the Samoidae. That's a really interesting pattern that we'd like to go and get some samples from the islands of Fiji and Samoa to see when this divergence really occurred and try to get a better date estimate there. And we go back to our question of, are islands the end of the colonization road? And the answer is no. Based on what we see in Neoscotolemon, we have evidence of reverse colonization. And so we have this out of Cuba hypothesis supported. And so it kind of shows that early on when you have these evanescent islands forming, if they persisted for long enough, for millions of years, you could have had species colonize them and then recolonize mainlands. And so that's really where you have the complexity in the Caribbean islands, and trying to figure out these patterns of evolution across the islands is an interesting kind of puzzle that we're trying to piece together. So with the future directions of this, we're looking at scaling up and improving taxon sampling. We would really love to sample from parts of South America, Colombia, and Venezuela, all through the Guianan Shield, even out into Ecuador. It would be great to have samples from all those places. Fiji and Samoa, obviously, to try and look at that cross-Pacific dispersal, and as well as trying to get more of the sister lineage of Piantidae from Africa, which we know that some of these existing collections, we know that MCZ has collections of harvestmen from Fiji. We know that the AMNH, the American Museum of Natural History, and the California Academy of Sciences both have specimens from Africa. So going to those collections and utilizing those collections will be an important next step for us. We also would like to look at total evidence dating, trying to create a character matrix for the morphology, and trying to place the fossils into that as terminals, and then analyzing the data to see exactly how that compares to our previous analyses. So these are kind of next steps, as well as scaling up to phylogenomics. So I'd really be interested in using ultra-conserved elements, which produces thousands of markers. It can resolve both deep and shallow divergences, and they're available now for mammals, birds, reptiles, fish, arthropods, and as of last year, there is an ultra-conserved element probe set that has been designed for arachnids. So that's really exciting, and I hope to be able to use this method to see how we've done with our multi-locus phylogeny. So that's kind of where I ended with my postdoctoral work. But I wanted to present to you a little bit of what I presented last week at the Arachnology Conference in Querétaro, because it's more relevant to people working here in Mexico, because this group is very diverse in southern Mexico, in Chiapas, Oaxaca, Veracruz, and out into the Yucatan Peninsula. So I just want to give you kind of a taste of what I'm working on, why I'm here at the collection and looking through the collection, what I'm looking for. And maybe the next time I come back, I'll be presenting more results on this particular study. So we're looking at now the family Cosmetidae. It's a very diverse group, also neotropical. And in particular, I'm looking at this genus Ergonulus, which is distributed from southern Mexico down to Costa Rica. And so first, just let me go through and say a little thanks to, I think I missed my acknowledgement slide in the last one, but I don't know how I skipped over that, and it should have been at the beginning. But I'll just say thanks to the people of Cuba, who I collected with back in December, Abel, who I worked with in Argentina, a friend at App State, who I used his lab and some of the equipment there. Lots of participants who helped collect specimens over the years. Of course, the people who organized the meeting last week. That's why I came down here, and now I'm staying to look at the collection, so I'm excited to be here. And then Jesus, Gerardo, Oscar, and all the lab here who have been kind enough and helpful in allowing me to look through the collections for this genus Ergonulus. And so here you see two of the cosmetids, very bright, very colorful, very diverse, all through the neotropics. Okay, so we're kind of switching from the superfamily Samoidia over to Gonoleptoidea. Now this is a very diverse group with more than 2,000 species described, and Cosmetidae is my focus with over 700 species described. So this is a very diverse group, and the taxonomy and systematics is a mess. And so that's why I'm kind of here to gather up some specimens and start working on this group again. They're very colorful, lots of color patterns, spines on the dorsum, quite large animals, much larger than the ones that I was working on for my postdoc, the Samoyedea. The Cosmetidae are much larger. Okay, so just to give you an idea of the diversity in the neotropics. In a study that I did at La Selva Biological Station in Costa Rica, we have 38 species that we found and documented there, half of which are undescribed. And half of the species that are there are actually made up by Cosmetidae. So 50% of the species diversity at one single site is made up by Cosmetidae. And you can see in the yellow box on the left and the 3 boxed in yellow on the right here, those are all the Cosmetids. Very diverse in terms of dorsal color patterns, spines on the back. But with so many species, the taxonomy is difficult to really sort out. There's also things that we don't know about them, for example, about their natural history. So in this particular animal here is a male guarding eggs on the underside of a leaf. We described in 2011 this first case of paternal care in Cosmetids. But this species remains undescribed. We attempted to describe it, but we don't know what genus to place it in. So it's kind of a mess, and it really prevents us from studying other things. This mess of the systematics really prevents us from studying other things about the animals, especially about their natural history, reproductive behaviors, etc. So within the family, with those 729 species, 127 genera, half of the genera, more than half of the genera are monotypic. So those genera only have one species, yet the top 6 genera in the family contain more than half of the diversity. So we have Cynorta, 150 species, Pysolema, 93 species. We have this kind of imbalance in the taxonomy, and it started with the early taxonomists and the way they classified these animals. And so two of the groups of people that did early taxonomy of the Cosmetidae are Rover and the Goodnights. And they kind of had and Rover described 288 species of the Cosmetidae. So he has described many more than anyone else. The Goodnights come in second with 87, but they took very different approaches. We have the lumpers and the splitters. Rover designed a system where he used a set number of characters, and 2 of those characters are the armature of the 4 scutal areas and the tarsomere count. So he said if there's, and he used leg 1 tarsomere. So he said if leg 1 has 5 tarsomeres, and the armature on the scute is spines on area 1 and area 3, that's one genus. And if the spines are on areas 1, 3, and 4, that's another genus. And if they're only on 3 and 4, that's another genus. So you can see how we quickly get to the point where we have lots of monotypic genera. The Goodnights, on the other hand, came up with a classification system where they said, let's forget about the dorsal armature, let's just focus on the tarsomere count on leg 1. So they said all species that have 5 tarsomeres on leg 1 belong to the Nones. And they took species from 24 genera and synonymized them into 1. And they took species from 28 genera and synonymized them into Cynorta if they had 6 tarsomeres on leg 1, and Pysolema if they had 7 tarsomeres on leg 1. So they saw, and they did this for all the Mexican Cosmetids. So they saw only 3 genera instead of some 50-some genera. So a very extreme example on the other end. That was rejected, and we went back to the Roverian system. So the way we classify things today is still under the Roverian system. And so we still have a bit of a mess to sort out. So with modern systematics, we're looking at more characters than those authors. We're looking at body shape, sexually dimorphic characters, the armature of the palps and clerestory, and a very important one, the genitalic morphology. It turns out that many species in Cosmetidae have this very conserved morphology where you have here's the penis, this is the ventral plate, it's kind of rectangular. This is the dorsal side, so we have the glands of the penis. We have this dorsal thumb-like process, and then we have the stylus, which can be adorned with spines. So this is kind of the blueprint for most cosmetics. So it was a surprise when we looked at the genus Ergonulus, and we're calling them the misfits because we looked at them, and here's two species that look relatively similar with external morphology. They're obviously cosmetids. The pedipalps tell us that. The biggest difference between these two species is in the leg armature. So here we have armature on the femur of leg 4. Here we have it in the tibia of leg 4. So subserialis is on the femur is armed, claviotibialis, as the name implies, the tibia is heavily armed. So we looked at the genitalia of these, and in subserialis we have one penis morphology that's very different from typical cosmetids. Here, a typical cosmetid, in Ergonulus subserialis, we have the ventral plate, which is bent over and curved so that it forms this kind of depression on the tip, and the glans is kind of hidden underneath that. We also have this area of what appears to be softer tissue, which is probably inflatable. We can't tell that based on SEM. We'd have to expand it and look at it under a compound scope, but it appears to be inflatable. So this is a very different morphology from other cosmetids. Again, this is the one with the leg 4 femur armed. In claviotibialis, we see a completely different morphology yet again, something unlike all cosmetids and unlike all other monoleptoids. Normally we have a ventral plate that attaches directly to the truncus. Here we have a ventral plate and a pseudo-ventral plate, which is an extension of the truncus. So it's almost like a double ventral plate. And this is just incredibly different from any other gonoleptoid harvestman. And yet we know it fits into this family Cosmetidae. So what I've done is I've come to this collection and I've been looking through all the materials from Chiapas and Oaxaca for specimens that represent both of these morphologies. And it turns out what I'm finding is that the species that have the femur armed typically have this morphology. The species that have the tibia armed typically have this morphology. So there's some correlation between those two characters. And if we go back to looking at their external morphology, they're very similar. So we have a very incredible convergent morphology in the exomorphology, or a very incredibly divergent morphology in the penis morphology. So we have begun to collect some molecular data for cosmetids, but we don't have Ergonulus yet for molecular data. And now that I've looked through the collection and some of the fresher materials here, I do have Ergonulus, and I'll go back and get that data and be able to fit it into this molecular phylogeny to see where they fit. But we're not sure based on the genitalia morphology where they belong. It's possible that this form is similar to this Metalabidia, which is an early divergent lineage of the Cosmetidae, based on these kind of inflatable sacs. So these might be homologous to inflatable sacs that's in Metalabidia, but this particular morphology could fit anywhere within the other group of cosmetids, the kind of standard cosmetid morphology. So again, looking at that external morphology, just incredibly similar, and yet the penis morphology tells a whole different story. And then, looking back at the systematics again, in this tree I have two species of Cynortillana, it's not monophyletic. I have two species of Pysolema, it's not monophyletic. So clearly the Roverian system isn't forming natural groups that reflect the true evolutionary history of these animals. And so we're trying to sort of revise the genera and look at what characters really define a genus. And I think Ergonulus is a good place to start, given their very distinct penis morphology. And so another good place to start is in the Caribbean islands, going back to the Caribbean island biogeography, because cosmetids are also all through those islands. So I took 3 species that I collected from Cuba last December and put them into this molecular phylogeny. And we see that these 2 species quite similar all around, the spines on the dorsum very similar, but this 3rd species has tubercles on areas 1 and 2 and spines on areas 3 and 4. So it's a very different armature pattern compared to these, which have tubercles on 1 and spines on 3. And yet we see them forming a monophyletic group within Cuba. So the islands could be a great place to start revising taxa because we can more safely assume that species on one island are more closely related, and we might be able to start there with redefining the genera. Okay, well, I will take any questions. I hope I didn't roll through it too quickly.
Maybe I can start maybe.
Yeah.
I was very, thank you Dan for magnificent talk.
Oh, yeah.
It was very interesting. In the first part of the talk,
Yeah.
you mentioned something about these particular patterns of dispersion from America to this Fiji Islands
Yeah.
and everything. So I was wondering about the timing because particularly the previous colonization of the other family that has a similar pattern of distribution
Yeah.
was about 80 million years ago.
Right.
And apparently the one that you were checking was more present.
Yeah, it
or
seems
at
that
least
way.
seems that way.
Yeah.
Do you think that there could be a kind of exclusive competition that reduces the diversification patterns in the second colonization?
Yeah, quite possibly. The only place that we're certain that they exist, that both families exist, is in Fiji. I'm not sure that the Zamoxids are in Samoa, and we don't know of any Samoids that are in other islands where the Zamoxids are. So maybe competition in the islands prevented them from successfully colonizing more of the islands in the Pacific. That's quite a possibility. It's also possible that the age estimates for the Zamoxids are a bit older than they truly are. It might be overestimated.
Yeah, I was wondering because maybe considering the current patterns of distribution, if there is a lot of sympathy or co-occurrence between different families in the same place.
Yeah,
it's
so
kind of,
in the neotropics there is. In the neotropics both families exist, and there's a lot of syntopic species there. But in the Pacific Islands, we don't know of very many overlapping patterns with these 2 families.
okay. And in the second part of your talk, I was very interested in these convergence patterns in some morphological traits.
Yeah.
It seems for me like maybe it could be effectively very plastic morphology that has this convergence are associated with some kind of habitats or habitat.
Yeah, very much a very good possibility. I think what's interesting is that the species, the 2 forms that I showed, one of them, they're both in Chiapas and Oaxaca, but one of the forms, this form, is in Chiapas, Oaxaca, and then extends down. We know that this occurs in Nicaragua and Costa Rica, but this form, we only know that it exists in Chiapas, Oaxaca, and into the Yucatan and in Belize. So it seems that they're overlapping in Chiapas and Oaxaca, but from there they've sort of dispersed different directions. But we're not sure because, for example, in Costa Rica we know of 125 described species in Nicaragua of Laniatories harvestmen. In Nicaragua we know of 2 described species in Nicaragua. So no one has really studied the harvestmen there. There could be lots of different patterns that we don't know about from between Chiapas and Nicaragua.
Okay, thank you.
Yeah. Yeah.
$50,000 question.
Yeah.
How can 2 families, little itty Opiliones, disperse from Central America to Fiji and Samoa, and they missed Kauai.
Yeah,
How could they have missed Kauai?
I know.
It's much closer to Hawaii.
Yeah.
It's, well, considering that the Hawaiian Islands are much younger, and these dispersals to the Pacific Islands may have happened tens of millions of years ago, even though there are older islands in Hawaii that have since been inundated, the oldest island currently in Hawaii at 5 million years is much younger than the Pacific Islands.
But the oldest submerged island in the Hawaiian chain is 80 million years old.
Yeah, that's true.
They
could have
emergent
reached-
land.
They could have reached Hawaii at some point and gone extinct. You know, they didn't colonize
Jumped
the islands, you know, like they're seeing the patterns in Hawaii, this island hopping down the chain as the islands form. Maybe they weren't successful. Maybe they did reach Hawaii at some point, but they didn't successfully move on to
They're
the
not
next
in
islands.
Galapagos either.
There's two species in the Galapagos. Two
Those
species.
meadows.
No, not cosmetics. I think one got elected, and maybe one's elmoxid. Yeah, I think. Yeah, but very few species there.
Another question? Well, thank you
All right.
very much, man.
Thank you.